Well, hello, AP Physics students. Mr. Curse coming at you here, and we are going to talk about sound today. All right, so the very thing we're talking about is what you're using right now to hear my voice. So, what is sound? Well, sound is a longitudinal wave, right? Sometimes called a pressure wave. Which means it's not a transverse wave that goes up and down. You guys remember kind of what a transverse wave looks like, right? The medium is going up and down while the wave propagates this way, right? Sound is a longitudinal wave or a pressure wave. There's a nice little picture in your book showing you just a reminder of what a longitudinal wave is. If you think about a bass drum beating, the bass drum vibrates back and forth, and it makes compressions or high density, high pressure areas, and refractions or low pressure areas. Right? So sound is a wave. All the normal wave phenomena about interference and diffraction apply to it. And it's a longitudinal wave. So that's one of the first things you'll want to keep in mind about sound. So sounds come in many frequencies or many vibrations per second, but the human ear can hear from about 20 hertz up to about 20,000 hertz. Now, the older you get, your range of hearing on the high end actually gets lower. Tomorrow in class, we're actually going to do a little demonstration, and we'll see how high a frequency everyone can hear. But the human ear can hear sound from about 20 to 20,000 hertz. And then obviously there's animals, for instance, dogs can hear much higher than that, and whales can hear lower than that. Sound above 20,000 hertz is called ultrasound. Sound below 20,000 hertz is called infrasonic, right? So we've got ultrasound and infrasound. Okay, so mom and dad are mad at you because you're playing Taylor Swift just way too loud, right? You got some blank space going on, and it's just way too loud. And they say, hey, turn that music down, I can't hear myself think. So we're going to talk about what it means to have a loud sound. And there's a couple different terms that you want to be familiar with. First of all is the physics term, okay? So the physics term for how much sound there is called intensity. And it's measured in very physicsy units, watts per meter squared. So intensity is the rate at which energy is transferred. Remember, all waves transfer energy from place to place. They may not transfer matter from place to place, but they transfer energy. So in the intensity of a sound is measured in watts per meter squared. That's very much a physics term. Kind of like frequency is a physics term. Here, your band or orchestra instructor may not say, hey, change your frequency. He or she'll say, change your pitch. So frequency is very much a physics term. Pitch is how the human ear interprets that frequency. So intensity is loudness of sound. And actually, I shouldn't use that word because loudness is how we define how the human ear interprets that sound. Now, the reason we have defined a loudness scale is the human ear can actually hear a wide range of intensities. It can actually hear 10 to the minus 12th watts per meter squared, and then your ears will start experiencing pain at like 10 to the second. So that's like a range of 10 to the 14th. 14 orders of magnitude. That's a huge range. So it's not very convenient to talk in those units in terms of human perception. So loudness has a different measure. So loudness is the human perception of intensity, and it's in the units that you're probably more familiar with, the decibel. Okay? So what is a decibel? Well, number one, we're running out of unit or letters here. So we're going to use the Greek letter beta. That's a beta there. Kind of looks like a B. To represent decibels. Okay. So decibels is equal to 10 times the log of the intensity of the sound divided by I naught. And I naught is called the threshold of hearing. Conceptually speaking, I naught is the softest sound that a healthy, focused human ear could make out. All right. So the quietest sound you could hear is about 10 to the minus 12 watts per meter squared, which, if you really stop and think about that, that's pretty amazing that you can distinguish something, that's, a trillion times, trillion times softer than like 1 watt. So anyway, that's a very, very small amount of energy that your ears are able to detect. The human body is really a pretty amazing thing. So this is how we define decibels. That's the official definition. Sometimes it's nice when you're dealing with a new unit to just kind of take a look at what different things are. 0 decibels is the softest sound. That's the threshold of hearing. That's the softest sound you can hear. 10 decibels, 10 to 20 decibels, that's a whisper. Let's see, it goes all up to, the loudest noise you can hear without feeling pain is about 120 decibels. And sounds do get louder than this, but after that, your eardrums pretty much, are permanently damaged, and then you can't hear anymore. So anyway, notice here that when you go up 10 decibels, you go up a power of 10. So, for instance, let's take a look here. 40 decibels is actually 100 times more intense than 20 decibels. So it's a logarithmic scale. You guys have seen logarithmic scales before. Okay, on to the math. Problem number 9 in your book. Let's do problem number 9. It states that, let's read the problem for you here. Problem 9 states that what is the sound level of a sound whose intensity is 2 times 10 to the minus 6 watts per meter squared? So this is my physics intensity in energy units. What is that in decibels, right? So let's not give away our answer here. So that's the formula I want to use, and plugging things in. You guys can't see that. Plugging things in. That would be the formula I get, right? Here's my threshold of hearing. Here's the number that the problem gives me, right? And if I do my math correctly here, I get 10 times log 2.0 times 10 to the 6th. This will be, notice you can always check your answer. The log of 10 to the 6 should be between 6 and 7, right? So a number between 6 and 7 times 10, well, that's 63. So 63 decibels would be the loudness of a sound that is 2 times 10 to the minus 6 watts per meter squared. Okay, so no joke for you today. Sorry, ladies and gentlemen, no joke. Instead, I have a book recommendation for you. This book I am just about to start reading. I'm very excited about it. It's Sam Keen, and the name of the book is The Disappearing Spoon, and Other Tales of Madness, Love, and the History of a World from the Periodic Table of Elements. So, you should check out this book. My sister's read it. She just gave it to me. I'm very excited about it. Sam Keen is quite an author. He's worked for the New York Times, Mental Floss, if you guys are familiar with that YouTube app. And so no jokes today, just a good book recommendation. Wow, Mr. Kirsten, is that what you read all the time? Books about, chemistry? Well, I read books about chemistry periodically. You guys thought you weren't going to get a joke. I do books read books about chemistry periodically. That joke was pretty elementary, you might say. Elements. I said no joke. But then you got two jokes. Oh my gosh. Oh, but I know what you're thinking. Which of those two jokes was about the periodic table was more funny? Well, I thought they were equal funny, so those two jokes end in a tie. Because it's my necktie that has the periodic table on it. Because, yeah, that's what I do. All right. Good work, ladies and gentlemen. We will see you tomorrow.